Okay, you all welcome to Finite Element Analysis lecture. Today's lecture is the first lecture of this lecture series. Okay, Finite Element Analysis. Okay, the Finite Element Analysis is actually extremely popular in industry in nowadays. Every field, the civil engineering, mechanical, electrical, electronic, every field, there's a finite element analysis methods are using. Okay, so as a young graduates, engineering graduates, you must have a knowledge about this finite element method, and also you must have a practice finite element tool also. Okay, so then a finite element analysis. What is meant by the finite element analysis? A finite element analysis is a method of solving the complex engineering problem. Okay, it's a tool, it's a procedure, it's a method of solving governing differential equations. That means most of the engineering problem we can represent by a governing equations. Okay, the complex engineering problem, finally we end up with the governing equations of the problem. Okay, it may be a partial differential equation, it may be an integral equation, it may be a differential equation. Okay, so then if we can solve this differential equation, we can solve the problem also. Okay, then in most of the cases, analytical methods are not able to solve these differential equations. Okay, analytical methods are not able to solve this differential equation. In that situation, we need more powerful methods to solve this differential equation. Numerical methods, we have to go to the numerical methods to solve this differential equation in order to solve the engineering problem. So then the finite element analysis is one of the powerful method to solve these complex governing equations. Okay, actually it's a tool of solving the governing differential equations. Okay, actually this finite element analysis method having not more than the 70 years of history. The first paper was published on 1956 regarding to this finite element analysis. Actually, it having the not more than the 70 years of history. In early days, it's not this method is not popular because it needs a lot of computational effort. Okay, so early days, all the calculations done manually using the manual method used to calculate this to solve these algebraic equations. So the early days, this method was not popular, but the development of computer technology, the computational effort become less. With the development of computer technology, this finite element method become extremely popular in industry. Okay, that because the computational effort become less, so then the this method become more popular with the computer technology. Okay, in engineering field, day by day, our problem become complex. Okay, everyone tries to optimize their product in order to optimize the profit, in order to optimize the satisfaction of the customers, so that our problem become more complex. Okay, so that when the problem become more and more complex, available methods, analytical methods, not able to give solution for these problems. Okay, that's why we need the more powerful tool to solve this complex problem. That's why the finite element methods, finite difference method, finite volume methods, these kind of numerical methods come into play to solve these differential complex engineering problems. Okay, what happened in this finite element method is the complex engineering problem we can represent by a governing equation. Okay. Then if you can solve this governing differential equation, we can solve the problem also. When you are going to solve this governing differential equation, the analytical methods are not able to solve this differential equation. In that sense, what we are doing? We are dividing this complex problem to a subdomains. That means this considering domain, we are dividing into a subdomain. Then we are obtaining the equations for each and every subdomain. Okay, we are obtaining algebraic equations, simple algebraic equation for each and every subdomain. If you are dividing the domain to a n number of element, we are having the n number of algebraic equations. Okay, that means finally this complex problem end up with the set of algebraic equations, solving of set of algebraic equation. If you can solve this algebraic equation, we can find the field variable values for discrete points. Okay, field variable values in discrete points. So then intermediate points we can approximate using these nodal points values. Okay, this is the whole idea about this finite element method. This I will explain later. I will explain the complete picture of this finite element method. For the finite element analysis, there's a various approach. Among this approach, one of the main approach method is Galerkin's weighted residual approach. Okay. Then today's lecture is focusing to explain this Galerkin's weighted residual approach, how this method brought into a development of finite element analysis method. Okay, let's go to the today's lecture. Okay, finite element analysis. Okay, the finite element analysis, the first lecture of this lecture series. Today I am going to give the introduction to this. First of all, I am going to give the introduction to this subject, finite element analysis. So then, what is the basic concept behind this method? The basic concept behind this finite element method, first of all, I am going to explain. Well, let's take the example. Let's take the example. If we ask someone the area, how to calculate the area of this triangle by giving these dimensions a, then these dimensions are given, you can easily say this is the area of this triangle. Someone asks this rectangular area, you can directly say, if the dimensions are given, you can directly say area of this rectangle. If someone asks circle, the dimensions are given, you can directly say the area of this circle. Okay, you know this solve these problems. That means you know to obtain the solution for this problem. But someone says to find the area of this kind of problem. Okay, the semicircle. Okay, someone asked to find the solution for this kind of problem. What is that? Okay, what is that? Then you can say the problem become more complex. You can say the problem become more complex. Our regular methods, our direct method, there's no direct method to solve this problem. The problem become more complex. So what you are going to, how to solve this problem? How to solve this problem? What we are doing? We are dividing this complex domain to a subdomain. Okay, that means we are dividing this complex domain to a subdomain. Okay, then each and every subdomain we can obtain equations. We can obtain equations for each and every subdomain easily, because we simplify this complex problem to a non-geometrical shapes. Okay, non-geometrical shapes. That means for the triangle we can obtain the equations, and also the rectangle we can obtain the equations. For the circle we can obtain the equations. For the semicircle we can obtain the equations. So then what we are doing? We divide the complex domain to a subdomain. Then we are obtaining element equations for each and every subdomain. We are obtaining element solution for each and every subdomain. We are finding the triangle area of the triangle, we are finding the area of the rectangle, we are finding the area of the circle, we are finding the area of the semicircle. Okay, so then what we are doing next step, all these element solution we are assembled to obtain global solution. Okay, we are finding the element solution. Okay, then we are assembled to obtain the global solution. Okay, this is how we solve this kind of problem. The same thing we are applying in a finite element method. The complex problem we are simplifying, then we are obtaining the element solutions. That means we are dividing the complex domain to a subdomain. Then we are obtaining a set of algebraic equations. Then we are assemble all these element solution to obtain the global solution. The same thing we are doing in the finite element analysis method. That means finite element analysis method is a method of solving the governing differential equations. Okay, the complex engineering problem we can represent by a differential equation. So let's take the differential equation. Let's take the simple differential equation. Let's take this is the differential equation of a certain engineering problem. Okay, then solving this differential equation means we are finding the yx. Okay, so solving the differential equation means we are finding the solution, means we are finding the yx. How y is vary with the x. Okay, when you are going to find this in most of the cases we are not able to find the exact solution for the yx. In that sense we have to go to the numerical method. That means let's take this is how y is vary. Okay, this is the exact solution. Okay, let's take this is the exact solution. Exact solution. In most of the cases these exact solutions are not able to obtain. In that situation what we are doing, let's take this differential equation defined in between the, let's take this is the considered domain for the x. This differential equation defined in between this domain A to B region. Okay, the boundary values are given. Let's take the boundary values are given. Let's take y x is equal a is a known value. Let's take the y1 y a, y x is equal b. Let's take the yb. This kind of boundary values are given. So then this is ya, yb. Okay. Then when in a finite element method, what is happening? We are dividing this subdomain to a dividing this domain to a subdomains. Okay. Let's take we are dividing this domain to a subdomain. Okay. Okay. Then this is the, let's take field variable value at this point as the y1, y2, y3 and the y4. Okay, y4. Then we are obtaining algebraic equation which as the solution for this domain, each and every domain. Considering this domain, we are obtaining the algebraic equation from these two values, y1 and y3 values. Each and every subdomain we are obtaining this equation, algebraic equation representing. Okay, here you can see finally we end up with the set of algebraic equation with the approximate solution. Okay, we are obtaining the element solution which representing this kind of. Okay, then you can see these are unknown parameters, unknown values. These are unknown values. You can see y2, y3 and y4. These are unknown values. By solving this set of algebraic equation, we are able to find this y1, y2 and y3, these unknowns. Okay, that means the field variable values in discrete point we can find by solving this set of algebraic equations. Okay, then if you know this field variable value in this discrete point, we can closely approximate intermediate point using the interpolation functions. Using the interpolation functions, we can closely approximate this intermediate point using these known nodal point variable values. Okay, if we can divide this domain to a higher number of elements, what happens? Obtaining the number of algebraic equation also increases. Then what happens? We can closely approximate the problem. Very closely approximate the problem. Then the accuracy increases. That means more accurate result we can obtain if we can divide this domain to a higher number of elements. Then what happens? Number of algebraic equation also increases. If we divide the domain to a n number of elements, we are having the n number of algebraic equations. Okay, we have to solve the n number of algebraic equations. What happens if we are dividing the domain to a higher number of elements? That means that become the computational effort become more high. Okay, but we can get the very accurate result. Okay, this is the whole idea about this the concept of the finite element analysis method. Okay, then this for the finite element method, there's a two various approach methods. In this lecture, I am going to explain one of the main approach method is weighted residual Galerkin approach method. Okay, let's see this method. First of all, let's discuss about the weighted residual methods. Weighted residual methods. Okay, it's a method of solving the differential equation. Okay, let's take I'll explain this weighted residual method. Then we can go to the Galerkin weighted residual method. Then let's see how this Galerkin weighted residual method brought into development of finite element analysis. Okay, then let's take the, I'll explain this one. Let's take the differential equation. Okay, let's take the differential equation with the variable, then is defined in this domain. Okay, then let's take a boundary homogeneous, yeah, this is equal to 0. Then let's take the homogeneous boundary conditions are given. The y a is equal 0, y b is equal 0. Okay, in this method, what we are doing, we are approximate a solution. This approximate solution approximate solution, by looking at this differential equation, we are suggesting a approximate solution. By looking at this differential equation, we are suggesting a approximate solution. Approximate solution, let's take the y star, because it is an approximate solution. I will take the y star x. That is, we can write in this kind of format: sigma I is equal 1 to n zi ni x. Okay, these ci unknown parameters ci, these are called trial functions. Okay, these are called trial functions. This is the format of the approximate solution we are writing. You can use the polynomial as the approximate solution. You can use the polynomial also. That means most simplest form is the polynomial. Let's take c0, c1 plus c2x plus c3x square plus c4x into cube, like cn xn plus 1. Sorry, cn xn minus 1. You can use this kind of a polynomial as the approximate solution. Finally, after substituting the boundary conditions, you will end up with this kind of format. Okay, I'll explain that one. When selecting a approximate solution for this differential equation, there's three main consideration. This approximate solution should be a continuous throughout the considered domain. It should be a continuous throughout the considered domain. Okay, this solution should be a continuous throughout this domain. This is the domain we are considering, so it should be a continuous throughout this domain. Then the next consideration, it should satisfy essential boundary conditions. Okay, it should satisfy essential boundary conditions. These are the essential boundary conditions that are given. It should satisfy selected approximate solution should be satisfy essential boundary conditions. Okay? Then it should satisfy the physics of the problem. These are the three considerations. It should satisfy the physics of the problem. That means the selected polynomial should able to satisfy differential equation. In that sense, you have to select the approximate polynomial, approximate solution. Okay. Then because this is the approximate solution, what happens if we satisfy this differential equation by its solution? What happens? It will not equal to 0. Why? Because it is the approximate solution. What happens if we satisfy this differential equation from its solution? Okay, this is our differential equation. Okay. If you know the exact solution for this differential equation, yx, if you substitute this yx in this differential equation, that will give the 0. Okay, no problem. But we have only approximate solution. Okay. Then if we substitute this approximate solution in this differential equation, what happens? That will not equal to 0. Okay. That will not equal to 0 because it is the approximate solution, that something remaining. The remaining one is called the residue. Remaining one, that is equal to residue. Instead of equal to 0, it is equal to r residue. That is called residue. This is called residue. Residue. You know the word residue. Residue means something remaining after main part has gone is called the residue. Okay. The something remain after certain process is called the residue. In that sense, called residue in this process. That means if we substitute the approximate solution, we are remaining with the residue. Okay. So I will explain this. What is meant by this residue in a graphical sense? Let's take our x and the y. Then let's take this exact solution for this differential equation. But we are having the approximate solution. But it satisfies the essential boundary conditions. Let's take our approximate solution something like this. Okay, something like this. Okay, you can see for a certain point, you can see this is the residue error, residual error. Okay, residual error with the exact solution. Okay, our whole idea is to make a residue into 0. If we can make the residue into 0, we are reaching to the exact solution. For that, we are multiplying this residue with the weighting function. Then we are integral all over the domain. Then we are equating this residue to 0. In this weighted residual method, what we are doing? We are multiplying this residue with the weighting function. Then we are integral all over the domain. Then we are make this residue to this integral to 0. In that sense, we are finding the approximate solution constants. Okay, approximate solution constant we are finding to make this integral to 0. That is the idea of this weighted residual method. If we can find this unknown constant which can make this residue to 0, we are reaching to the exact solution. That is the whole idea of this weighted residual method. Okay. Then why we are multiplying this residue to weighting function, I will explain that one also. For example, what happens if we without multiplying the weighting function, if we integral all over the domain and make it to 0, when you are going to integral and make it to 0, what happens? Here it is a negative errors. Here is a negative errors. Here is a positive errors. Okay? Here is a negative errors. Here is a positive errors. If we take the R residual error, then integral all of the domain, that may be 0, but that will not represent, that will not reach to the exact solution. It doesn't mean it reaches to the exact solution. That is the problem. Okay, that's why we are multiplying with the weighting function. According to the selection of according to the selection of weighting function, according to the selection of weighting function, this weighted residual method has different methods. The first one, the least square method. Least square method, the Galerkin methods, Galerkin's method. The third one, the point collocation method. The fourth one, subdomain method. The various methods. Okay, according to the selection of the weighting function, the weighted residual method has divided into several methods: the least square method, Galerkin method, point collocation method, and subdomain method. So, but in this lecture is focusing to discuss the Galerkin method. We are going to discuss only these two, the least square method and the Galerkin methods, because the least square method is because the Galerkin method is a development of least square method, so we are going to discuss these two. Okay, these two methods. Okay, then let's move to this weighted residual least square method. Okay, the weighted residual least square method. Okay, let's take the differential equation as this one equal to 0. Let's take it is defined in between this region. Then the y x is equal a. Let's take the boundary, homogeneous boundary conditions are given. The y x is equal b, that is equal to 0. Okay, equal to 0. So then let's take this is the approximate solution. This is the approximate solution. Because this is approximate solution, if you substitute this approximate solution in the differential equation, dy star x, that will not equal to 0. That will not equal to 0 because it is approximate solution. That will equal to residue. That will equal to residue. Then residue is a that will not equal to 0. That will equal to residue. This residue, while the previous video also I have explained this what is meant by the residue. Let's take this is the exact solution. Then let's take this is the approximate solution. Y x. Okay, this is the exact solution. Approximate solution. This is the, sorry, let's take this is yx, then this is the y star x. Then you can see if we integral in this region, this residual error neutralize from the negative errors and the positive errors. Okay, that means we can't get the correct idea by integrating this residual in this region. Okay, because it neutralize the negative errors and the positive errors, neutralize the total error, so that we can't get the clear idea about the total error. So that what we are doing, we are integral, instead of taking the integral of residue, we are taking the integral of r square. We are taking the integral of r square dx. Then we are making this then we can get the total error with regard into this approximate solution. Let's take the total error as is. Okay, total error as is. So what is our effort is to minimize this. Our effort is to minimize this. Okay, the minimizing the total error mean we are reaching to the exact solution. We are reaching to the exact solution. Okay. So how to find the minimum of the s? What is the method to find the minimum of s? We are derivate and s. We are derivate that actually this s is a function of selected polynomial. I'll explain that one. This selected polynomial constant. That means this, let's take this is the approximate solution. I will explain. C1 plus C2x plus C3x square, like something like this is the approximate solution via V2. Okay, these are the unknown constant. These are the unknown constants C1, C2 and C3. That means Ci to Ci, the unknown constants. Okay, this residue also a function of these unknowns. Okay, if you take the residue, it's also a function of x, z1, c2, c3 up to cn. Okay, the residue also a function of x and c1, c2, c3 and cn. These unknown parameters. Then what we are going to do is we are going to minimize s. Then we are finding the c1, c2, c3 up to cn unknown constant which gives minimum s. Okay, which gives minimum s. That means we are finding this approximate solution parameters which gives minimum error. Okay, so then this function is this integral is a function of c1, c2 and c3 and cn. So what we are doing is we are minimizing the s with respect to each and every parameter. Dabba ci is equal to 0. Okay, that means we are minimizing the s with respect to each and every parameter of the approximate solution. Okay, then we can reach us to the exact solution. Okay, then when we are going to derivate with respect to each and every parameter, what happens? I am going to derivate this one. Dabba is over dabba ci is equal. Then we are going to derivate this integral a to b r square dx into dabba ci. Then this integral is defined to the variable of x. So then we can take this derivative inside to this integral because it is independent from the x. So that this equation we can write by derivating inside to r dabba r into dabba ci into dx integral all over the domain a to b. Okay, that means this is the dabba s dabba ci. Our effort is to make this one into 0. Okay, our effort is to make this one into 0. That means our effort is to make this one into 0. That means integral a to b 2r dabba r dabba ci dx we are going to make it to 0. Then you can see this equation we can simplify. 0 integral a to b r dabba ci dx. Okay, this is the finally end up with this equation. You can see we are finding the approximate solution constants. Approximate solution constants. Approximate solution constant, this C1, C2, C3 constant, in order to make this equation to 0. Then in this least square method, this is the weighting function. The least square method, this is the weighting function Wi. If there is a n number of constant parameters, we are having the n number of weighting function. We have a n number of weighting functions. Okay, so then what happens? If you are having the n number of weighting function, we are having the n number of equations, n number of algebraic equations. By solving this integral equation, we are finding the n number of algebraic equations. Okay, that means by solving this n number of algebraic equation, we are able to find these each and every constants, C1, C2 and up to Cn constants. That means we are finding the approximate solution which minimizes the total error. That means we are close into the exact solution. That is the whole idea about this weighted residual least square method. Okay, let's understand this this method through the example. Okay, then you will get more clear idea about this least square method. Let's take the simple example problem. Okay, the example problem. I'm going to write the question. The obtain an approximate solution for the following differential equation using the weighted residual least square method. Okay, then this is the differential equation. Okay, obtain an approximate solution. Using the weighted residual least square method. So then this function is defined in between the domain 0 to 1. Okay, then the homogeneous boundary conditions are given. The y x is equal 0, 1, y x is equal 1, that is equal to 0. Okay, that is equal to 0. Then as the approximate solution, then y star x is equal to, as the approximate solution I am taking second order polynomial. Okay, the you can say c1 plus c2x plus c3x square, then plus c4x into 3. Yes, the third order polynomial. Here we can see consider third order polynomial as a in generally to get the reasonable accuracy. The order of the differential equation in the second order differential equation n is equal to, when selecting the approximate solution, we are taken n plus 1 polynomial. That means we are taken the third order polynomial generally. Okay, you can lower the order of the polynomial. That doesn't matter. If you are lowering the order of the polynomial, if you take the second order polynomial, what happens? If we end up with this point, you are getting the solution but lesser accuracy. You can increase the order of the polynomial also, then we will get the more accurate result, but the computational effort become very high. Okay, so lowering and you can lower, and also you can increase the order, but you will end up with the different accuracy result. Okay, then as a generally we are selecting the polynomial up to third order polynomial. It's the one greater than the order of the differential equation. But in this situation, I am going to take the polynomial up to this point because the considering the easiness of the calculation. Okay, to have the lengthy calculation, so I am going to take the approximate solution yx as is equal c1 plus c2 x plus c3 x into square. Okay, this is the approximate solution I am selecting, second order polynomial. You can check this result also with the third order polynomial. Do it as a homework. Okay, let's take I am using this one. So then the approximate solution should satisfy the essential boundary conditions. What are the essential boundary conditions? Selected polynomial should satisfy the essential boundary conditions. X is equal 0. This one is equal to 1. So then x is equal 0. This equals c1 is equal to 1. We have in the equation unknown constant. The c1 is equal to 1. Then x is equal 1. That is equal to 0. Is 1 plus c2 plus c3. So then c2 we can write the c2 is equal minus 1 plus c3. Okay, it should satisfy. In that sense, we have to select the unknown parameters, which this selected approximate solution should be able to satisfy the essential boundary condition. In that sense, we have to select the unknown parameters. So then finally we can write the approximate solution which satisfying the boundary conditions. Then 1 minus x by avoiding this c3 c square minus 6 c square minus 6. Okay, this is our approximate solution which satisfying the essential boundary conditions. Okay, we have one unknown parameter. We are having only one unknown parameter. So if we select the third order polynomial, you will get the two unknown parameters. But in this situation, we are having the one unknown parameter. Considering the easiness of the calculation, I took this second order polynomial. Okay, this is our approximate solution. Then I am going to substitute this approximate solution in the differential equation in order to find the residue. So let's take, before going to this substitute in the differential equation, d2yx, let's take the dx, first derivative minus 1 plus c3 2x minus 1. Then the second derivative of the approximate solution d2 y star x dx square, that is equal to, the second derivative is equal to the 2 into z3. Okay, then I'm going to substitute this, I'm going to satisfy this differential equation in the d2y dx square plus y is equal to 1. So then if we substitute that by taking this 1 into one side, d2y dx square plus y minus 1, that is equal to 0. If we substitute the approximate solution, what happened? d2y star x dx square plus y star minus 1, that will not equal to 0 because it is the approximate solution, that will equal to residue. So that the residue is equal to this one. What is our second derivative we obtain? 2 into c3 plus the, what is our approximate solution? What is our approximate solution? This one, 1 minus x plus c3 x square minus x, then the minus 1. Then we can residue we can is a function of x comma c3. You can see is equal to, finally we end up with the minus x plus c3 into x square minus x, here. Yeah, here it is 2, no? Plus 2. We end up with the residue as this kind of function. Okay. Then according to the least square method, this is our least square method. Previously we discussed. What is our weighting function? Our weighting function, we are obtaining derivating the residue with respect to the each and every unknown constant of the approximate solution. So here only we are having the one constant c3. So in order to find the w, only one weighting function, because only one variable, w1 is equal daba r into, what is our unknown parameter? ci c3. Okay. Then if we derivate this function to a 1, we are getting c3. We are derivating with respect to the c3. So then we are getting s square minus x plus 2. This is the weighting function in our weighted residual calculation. Okay, in least square method. Okay, then what we are doing? We are making this one into 0. Integral 0 to 1, considering domain the differential equation defined in between this region. So w1r dx we are going to make into 0. In that sense, we are finding the c3. Okay, which gives this integral to 0. Okay, so then I am substituting these values 0 to 1. I am substituting these values. What are w? X square minus x plus 2 minus x plus c3 x square minus x plus 2 equal to 0. Okay, then I am going to simplify this, expand this solution. Then we can easily integral this one, the 0 to 1. You can easily integral this one. Yeah. Minus x into cube plus x into square plus minus 2x plus c3 x square minus x plus 2 into square is equal to 0. Okay, so then we can expand this one also. We have to expand this one also. Expand that one also. Integral 0 to 1 minus x into cube plus x square minus 2x. So I'm going to expand this term, x into 4 minus 2x into 3 plus 5x into square minus 4x plus 4 into dx is equal to 0. Then now we can do the integral easily. Minus x into 4 divided by 4, 0 to 1, plus x into cube, x into 3 divided by 3, minus 2x into square divided by 2, plus c3 x5 divided by 5, minus 2x into 4 divided by 4, plus 5x into 3 divided by 3, minus 4x into square divided by 2, plus the 4x into 0. Okay, then I am going to substitute the integral limits. So then we are getting minus 4 plus 1 over 3 minus 1 plus c3 1 over 5 minus half plus 5 over 3 minus 2 plus 4 equal 0. Then you can use your calculators to find this c3. The c3, I am getting the answer 0. For the c3 I am getting 0.2723. please take the value. Then this is the c3. This is how we are finding the unknown constant, which gives integral to 0. So then our approximate solution by star x. What is our approximate solution? Our approximate solution 1 minus x plus c3 x square minus x. This is our approximate solution. Then this approximate solution, I am going to substitute this found c3 value in this equation. Y star x, that is equal to 1 minus x minus by simplifying this equation 0.2723x plus 0.2723x into square. Then finally we are end up with this solution 1 minus 1.2723x plus 0.2723x into square. This is the approximate solution we found for this using the weighted residual least square method. Okay, this is the least square method. Then I think you all get the more clear idea about this least square method. Then let's move to the Galerkin methods. Okay, let's move to the Galerkin methods. Okay, let's move to the weighted residual Galerkin methods. Okay, weighted residual Galerkin methods. Then approximate solution for the differential equation, the area I explained. We can write it using this kind of format, sigma I is equal 1 to n ci n ix. Okay, we can write this approximate solution in this kind of format. In the previous example also you can see you can write in that manner. Okay, these are called trial functions. Trial functions, these are unknown constants, constant parameters, unknown constant parameters. In the previous example also we can you can see these unknown parameters. This is the approximate solution. We can write this approximate solution here. The 1 minus x plus c3 x square minus x. Okay, then here it is actually the c1 is equal. You can see this is the format of approximate solution. Sigma I is equal to 1 and ci nix. Okay, then these are trial functions. These are unknown constants. Our effort is to find this unknown constant which minimize the error. Okay, here we discussed the least square method. Then we are going to discuss the Galerkin methods. Okay, this is the approximate solution general format. Then in this Galerkin method, weighting function wi are the derivative of the approximate solution function with respect to the unknown parameter. Okay, this is very important. Weighting function wi are the derivatives of the approximate solution approximate solution yx with respect to unknown parameters. Okay, the weighting functions are the derivatives of the approximate solution with respect to the unknown parameters. If the unknown parameters, if approximate solution having the n number of unknown parameters, we are having the n number of weighting functions. Okay, n number of weighting functions mean we are having the n number of algebraic equation to find the n number of unknown constants, unknown parameters. So that means wi we can define that in this way is equal daba y approximate function into each variable daba ci. Okay, this is how we are finding the weighting function in Galerkin's weighted residual method. Okay, this is how we are selecting the weighting function in the Galerkin method. Actually, this Galerkin method is a development of least square method. In a least square method, actually this Galerkin method is a development of least square method. Rather than use of derivative of the residuals with respect to the unknown constant, the derivative of the approximate function is used. Okay, derivative of the approximate functions are used. Well, let's take the example. Then let's get the clear idea about this Galerkin's weighted residual method. Example, Okay, let's take the previous example, same example. Use the Galerkin method to solve the problem. Use the Galerkin method to solve the following problem: d2y dx square plus y. Previous example, same example. This is defined. Sorry. This equation is defined greater than x less than 1. The y x is equal 0, that is equal to 1. Y x is equal 1, that is equal to 0. Okay. So I took the previous example. The same as I'm going to use the approximate solution. Y star is equal c1 plus c2 x plus c3 x into square. Okay, you can use the higher order polynomials, no problem. If you are taking the higher order polynomial, you will increase the accuracy. Okay, if you are selecting the lower order polynomial, mean you are reducing the accuracy. Okay, then this equation, previously we rearranged this equation by substituting the boundary conditions. Because this approximate solution, it should satisfy the essential boundary condition. In that way, we have to select the approximate solution. After substituting the boundary condition, this equation has reduced to this kind of manner. In the previous example, I explained this one, minus 6. Okay. Then these are the trial functions. Here you can see the two different trial functions we are having. These are the trial functions. The two trial functions. Actually, these trial functions come as the weighting function in a Galerkin's method. I explain that one. Then here only one unknown parameter. So then how to select the weighting function? Because only one weighting function, so that is equal to daba y star daba c3. With respect to c3, I am going to take the partial differential. With respect to c3, I am going to derive this approximate solution. Then we are getting x square minus 6. This is our weighting function. In this Galerkin method. Then I will write the residual equation. Between we are going to make wx into rx, dx equal to 0. Consider the entire domain. Okay, consider the entire domain. What is our wx? So I will directly put this equation in this substitute the equation in this equation, because we have already found this rx in the previous example. Rx same, the x square, only difference is the selection of weighting function. The rx we have already found that in the previous example, minus x plus c3 x square minus c3x plus 2c3 into dx integral, what is the considered domain, 0 to 1, that is equal to 0. Okay, that is totally equal to 0. Okay, so then I am going to do this integral. Before in this integral, I am going to multiply by this. We can remove this bracket. Minus x into cube plus c3 x into 4 minus c3 x into cube plus 2 c3 x into square plus x into square minus c3 into x into 3 plus c3 into x into square minus 2 c3 into x into dx. Okay, then we can easily do the integral. Okay, so then finally, after x4 divided by 4 plus c3, yeah, it is minus, no? 0 to 1, c3 x into 5 divided by 5 minus c3 x into 4 divided by 4 plus 2 c3 x into 3 divided by 3 x into cube divided by 3 minus c3 x into 4 divided by 4 plus c3. Okay, then I am going to substitute the limit for this equation. Minus 1 over 4 plus 1 over 5 into c3 minus 1 over 4 into c3 plus 2 over 3 c3 plus 1 over 3 minus 1 over 4 into c3 1 over 3 c3 minus c3, that will equal to 0. Okay, by making this simplifying, the minus 1 over 4 plus 1 over 3 plus c3 into whatever is the 5 minus 1 over 4 plus 2 over 3 1 over 4 plus 1 over 3 minus 1 into c3 is equal to 0. Okay. Okay, then finally the answer is so c3, we are getting the answer 0.2778. Then final answer we can write by star x approximate solution 1 minus x found constant 2778 x square minus x. So by star x, that is equal to so 1 minus 1.2778 into x plus 0.2778 into x square. Okay, this is the found solution for the Galerkin weighted residual approach. Okay, then this is the method we are used to come to the finite element analysis method. Okay, then on the next day class I will explain how this method, weighted residual Galerkin method, how this method brought into a development of finite element analysis technique. Okay, on next day class we are going to discuss that one. Okay, so enough for today. Thank you.